So before we get into the actual new stuff, now that we're done with the take-up, I do want to say a few things about the exam. So we've been working with frequency distributions. We are going to work with frequency distributions for the remainder of the semester. So I'm going to show you the performance of the class in terms of the frequency distribution. So here we have, here we have the grades for exam 1. So we got all the possible grades for exam 1. We got the frequency with which they occurred. And this is the frequency distribution that was obtained for exam number 1. So I'm putting this up here because I want people to use the feedback that they're getting from exam number 1 to kind of move forward and make sure that the rest of the course is really, really good. So if you are one of the people living in this apartment building on address 100%, congratulations, well done. Keep it up, keep doing what you're doing. Everything's working great. If you're one of these people over here, chances are you made a silly mistake, right? Chances are you jumped the gun on order of operations, or you used a manual entry instead of using the equals function. Whatever it is, probably was just a little slip of the wrist. So make sure that you identify it. Make sure that you know exactly what went wrong, because we want to turn everybody here into hundreds over here. 80s and 70s. If you're down here, typically this indicates that you got one question wrong, right? So you completely missed maybe question number 7. You might have completely missed question number 1. Or you missed a substantial part of more than one question. If after we took it up in class today, you're looking at the exam and you're like, oh, of course that's what I should have done. Oh my goodness, I can't believe I didn't do that. If that's you, and you know exactly what went wrong, keep going, keep working on it. We'll make sure that you move up here for exam number 2. If, on the other hand, you are still confused, right? So if you're still looking at question number 7 and you're thinking to yourself, I don't know what he did there, come see me, all right? We don't want to move off of exam number 1 without everybody here being able to get 100% on exam number 1 at this point. So again, if anything in exam number 1 is not making sense to you, come see me, come on, just drop on by. You don't even have to bring your laptop. I got everybody's exam on my files, and we'll just open it up and I'll take you through it. But let's make sure that moving forward, everything in exam number 1 makes sense. All right. If you're one of these individuals here, 2 things to keep in mind. Number 1, the course is not over for you. All right. So don't panic. Don't start, thinking about how you're not going to graduate. Don't start replanning your entire academic program. Don't think you're going to have to retake this course. Remember that there is a sliding scale in terms of how much exam number 1 is worth. So we'll make sure that this is your worst exam, and it's going to be worth, I think, what was it in the syllabus? Does anybody remember? It's like 5%, 6% of your grade. So even if you're down here, you've only lost 3% towards your final grade. So you can still achieve 90s in this course, all right? So first thing to do is take a deep breath, right? You got exam number 1 back. It didn't go the way that we planned. So take a deep breath, calm down. It's not the end of your semester. That's take home number 1. Take home number 2, though, is that something has to change. So this is not 1 or 2 silly mistakes. This is not kind of misunderstanding one of the questions. This kind of shows that something needs to change. So what we need to do between now and exam 2 is kind of figure out what needs to be done differently to move everybody here up here. So take a look at your exam, come to my office hours. If you're still struggling with z-scores, we need to work on it. We need to get that straightened out. If you're still struggling reading frequency distribution graphs, we need to get that sorted out. But basically, Again, remember, your semester's not over. You can still get a 90, 90s in this course, but do not think for a second that you can keep doing what you're doing. All right, something has to change. So if that involves coming to see me and we'll figure out what needs to change, do it. Make sure that you take care of it, because exam number 2 is coming up, and we definitely want to start moving everybody up to this area over here. All right, so that was exam number 1, and what we're going to do now is we're going to move on to our next concept, next thing that we need to learn in statistics, and we're ever moving closer to being able to do inferential statistics, which is the big magic in psychology, where we are able to take a look at a sample and intelligently generalize to a population. So we can study 20 people and help millions, but in an intelligent way. So we're getting to that cool stuff. We're getting to the point where we're actually going to be doing like real, psychology work, but we're not quite there yet. We just got a few more things to practice, and one of them we're going to be doing today, and it has to do with probability. So to just kind of set the stage for why we're doing this, why we keep practicing and practicing, and why we need this one last little fundamental idea, let's consider a situation that you might find yourself in when you graduate here and you get a job in the psychology field. Let's say that you are an educational psychologist and you're working with a group of students who are on the autistic spectrum, right? So they have autism, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 students in your class, 14 students that you're working with. And based on your education in psychology, based on your knowledge of how the mind works and how education works, you come up with this brand new idea. You come up with this idea where you say, you know what, maybe using interactive technology, maybe using learning devices that give you immediate feedback, that can tailor themselves to the child's interaction, that actually require interaction, would spur these children to actually interact with with the device. Maybe these new sorts of interactive learning would be beneficial for your students. So let's say that you implement this treatment, and by the end of the semester, you find out that your students have improved far beyond what they would have on a standard kind of textbook approach. So you have these 14 students, and you have this new technique, this new interactive teaching technique, and you know for sure, and this is the key, you know for sure that it has worked with these 14 students because you measured them before the semester, you did your treatment, you measured them after the semester, and it's very straightforward to say they're doing better after the semester than they were before the semester. We don't really need very much stats to make that determination. However, without inferential statistics, without the ability to generalize from these students, this is where our story ends. This is where your helping others ceases. Because when another parent calls you up and says, oh, hey, I have a child and they're autistic. I was wondering, can you recommend a program for me, for my child? Without inferential statistics, your answer will be no, I can't. I have a program that I tried, and I know it works on these 14 students, but if we're living in a world with no inferential statistics, for your student, for your child, can't make a recommendation. I have no idea. You could then say, well, let me test your child, and I'll try this out on him, and maybe it'll work, right? But then that would be limiting psychology to the very wealthy individuals that can afford private psychologists for their children. And we don't live in that world. So without inferential statistics, the parent who calls about their autistic child and says, can you recommend anything? Even though you're sitting on this gold mine of a treatment, your answer would be no, sorry, can't recommend it. And if a school calls you up and says, oh, we have children, in our program here who have autism, do you know of a treatment? or a program that can help them learn? Your answer would be no. And literally the entire population of autistic children who are out there showing, the can stacking, not interacting with others when they play, your answer to can I help these individuals would be no. You can help your 14, it works there, but does it work for anybody else? Does it work for the population of autistic children? Your answer would be, I have no idea. So you can see with this example, what we're working towards. We're working towards making psychology as useful as possible. We're working towards being able to make real differences in the world, because with inferential statistics, we can take a look at these 14 students and we can say, all right, this treatment worked for these 14 students. And with inferential statistics, I can also conclude that it will work for the population of autistic children as well. And that's where psychology gets its power to really help the entire population of individuals, not just the privileged individuals that happen to be in your particular study. So that's what we're working towards. And one of the last pieces of the puzzle, one of the last things that we need is probability. So we're going to do our introduction to probability, and we're going to take a look at probability in a new way, some way that you haven't considered it before, some way that's typically not taught in math classes, because this is probability for statistics. So we're going to link probability to frequency distributions, and this again is going to be your intro to probability. Next class we're going to delve into it a little bit deeper. All right, so 4 outcomes. You've probably seen something like this before, but if you have a set of outcomes that can occur, things that can happen, the probability of an outcome equals the number of successful outcomes divided by all possible outcomes. So the typical example of this is a coin flip. If you have a coin flip, you can either flip it heads or you can flip it tails. There are 2 possible outcomes. If you're going to win this horribly boring game that you're playing, but if you're going to win if you flip an H, right? That's one successful outcome. Flipping an H is a successful outcome. There's 2 possible outcomes. The probability of flipping that H, flipping that head is 1 divided by 2 is 50%. So that's the typical formula for dealing with probabilities. Probability is so incredibly important in statistics that it gets its own symbol, the symbol P there, P for probability. And this is immensely important in psychology, because this is going to be what we base our decision on when we're doing inferential statistics. So if you ask any of the psychology faculty here to tell you what a p-value is, they will know that for sure. And when we do our experiments, we sit there doing our stats, and we're hoping for a low p-value. And you'll find out why later on, but that it's the almighty p-value. And we're like, oh my gosh, I hope a p-value, I hope we get less than 0.05. What did we do for our experiment? What's the p-value? 0.03. Yes, awesome, we can publish. Versus, what's the p-value? 0.09. Oh no, right? There's a difference. P-value is very important. So this is why we're looking at probability as that last piece that we need for inferential statistics. This is the mathematical way of thinking about probability, right? This is probably what you've encountered before in math class. This is not the way we're going to do it, though, in stats. Because in statistics, probabilities are going to be equivalent to proportions. So probabilities are going to be equivalent to pieces of something. And you'll see what that something is in just a moment. So to put a little bit more, to make it a little bit more complete, this explanation, for any outcomes that are classified as A, B, C, or D, so generalized, beyond the 2 outcome formula here, for any number of outcomes that you have, the probability of one of those outcomes occurring, so this is read as the probability of A happening, The probability of A happening equals the number of outcomes that are classified as A divided by the total number of possible outcomes. So this, again, don't read it as P, read it as probability. This is the probability of A occurring. But what probability? How are we going to understand this? Once again, probabilities are not equal to decimals, not equal to fractions. They're equal to proportions. So what is it equal to a proportion of, you ask? It equals to a proportion of a frequency distribution. So we are not done with frequency distributions by a long shot. This is where our knowledge of frequency distributions is going to come into play, because we're going to see that probabilities are pieces of these frequency distributions. So let me show you how this might work. And we'll go to the other textbook example of probability, which is rolling a dice. So when you're rolling a die, in this case we'll just talk about the one, there are certain outcomes and they'll occur with certain frequencies. So let's say that you rolled a dice, what did I use here? Let's say that you roll it 6 million times. All right, let's say that you have nothing to do on your hands, but go to Monte Carlo, observe, the rolls of the dice, and you're just sitting there with your notepad saying how many times the different values come up when a dice is rolled, and you do that for 6 million rolls. Incidentally, they used to do that. It's called the Monte Carlo experiment because of those casinos, and that's where a lot of the initial studies on probability in terms of gambling and casinos actually came from. So they actually had people sitting there going, what numbers come up on a roulette wheel? And they would just write it down. All right, so let's say that you do that. You would find out that the outcome 0 never occurred, right? You're not going to roll a 6-sided dice and get a 0. You might find out that the outcome of 1 happened just over 921,000 times. About just over 1 million times, they rolled a 2. 921,000 times they rolled a 3. 995,000 times they rolled a 4. Over 1 million times they rolled a 5. Over 1 million times they rolled a 6. And they never rolled a 7. If you ever roll a 7 in a casino, you're going to get arrested with a single dice. Anyways, those are the outcomes if you looked at it 6 million times. Because those numbers are just too huge, right? They're too unruly to deal with. We're going to simplify them, and instead of the actual frequencies that came out, we're going to change these into expected frequencies, expected relative frequencies. And if you're dealing with a fair die, you're going to roll out of 6 rolls. You're going to roll a 1 on average 1 time, a 2 on average 1 time, a 3 on average 1 time, a 4 and a 5 and a 6. All of those are going to happen on average once if you're rolling a fair dice along the long term. All right, so that's the outcomes with their expected relative frequencies. So far, so good? All right, so what are the probabilities? So if we're going to use this probability formula, the probability is the outcome divided by the number of possible outcomes. We have a probability for getting a 0 of 0, right? There's no way to roll a 0. You have a 0% probability of rolling a 0 because it just doesn't happen. And it's how many outcomes are classified as 0? None. How many possible outcomes are there? 6. So we have 0 divided by 6 equals a probability of 0. To roll a 1, you got a probability of 1 outcome is classified as a 1. There's only 1 occurrence when you throw that dice, and the 1 side is facing up. That's the only way to roll a 1. 6 possible occurrences. 1 divided by 6 is 0.17. So this is a 17% chance of rolling a 1. And if it's a fair dice, there's also a 17% chance of rolling a 2, 17% chance of rolling a 3, 17% chance of rolling a 4, 5, and a 6, and again a 0% chance of rolling a 7. This is the mathematical way of thinking about probabilities. We're not going to do that way. We're going to do proportions. And proportions of what? We're going to do proportions of a frequency distribution. So instead of thinking about probability like this as decimals, what I want you to start thinking about it is in terms of proportions. So this is the frequency distribution graph of dice outcomes. So we expect 0 to happen, never. We expect 7 to happen, never. And we expect 1, 2, 3, 4, 5, and 6 to happen at the same expected frequency, which in this case is an expected frequency of 1. So this is how we want to think about probabilities. All right, so what benefit does this give us? Why are we trying to switch to thinking about probabilities in terms of a frequency distribution? Well, the reason that we're doing this is because it allows us to answer questions that come up in statistics very easily and very straightforwardly. So what do I mean by this? Well, let's say that you were playing a game. Let's say that you were with one of your nieces or nephews, and you were playing snakes and ladders, and you needed to roll an exact roll in order to win the game, and the number you needed was a 2. So you're sitting there 2 places from the finish, and you're playing that rule where you got to roll it exactly. What's the probability that you're going to win on your next roll? Well, there's one outcome that's classified as a 2, 6 possible outcomes, so that gives you a probability of 17%. You got a 17% chance that you're going to win on the very next roll. You can also answer that question with proportions. So if this frequency distribution is the entire collection of things that can happen, which is what it is, it's the entire collection of things that can happen, that blue area is the area where you win. And the probability that you're going to win on that next dice roll is the proportion of that blue area to the entire frequency distribution. And that blue area is 17% of that entire frequency distribution. So that was a pretty straightforward example. Didn't really buy much by taking a look at proportions. But what if it gets a little bit more complicated? What if somebody says to you, all right, I got this new game, and if you're going to win on your next roll, you have to roll an even number. So you got to roll a 2, a 4, or a 6. What's the probability that you are now going to win on your next turn? And this is when things start to get a little confusing if you're not well versed in probabilities mathematically. Because you might take a look at that and say, all right, there's a 17% chance I'll roll a 2. There's a 17% chance I'll roll a 4. There's a 17% chance I'll roll a 6. But I can win if I roll a 2 or a 4 or a 6. So do I add up those probabilities? Do I multiply those probabilities? Do I take 17 to the power of 3? What do I do here? How do I get that final answer? Because I know it's 17% to roll a 2, but I can roll a 2 or a 4 or a 6. What do I do here? It can get complicated. It can get confusing. It all goes away if you deal with proportions. Because if you deal with proportions of a frequency distribution, and you say, all right, if I roll a 2, I win. If I roll a 4, I win. And if I roll a 6, I win. Then that's the proportion of situations where I'll win on the next turn. And you look at that and you're like, oh, that's half of the entire distribution. So I got a 50% chance of rolling an even number. So that's why we want to switch to these proportions. The questions and the use of probability in statistics is better and more straightforward when you think about it in terms of proportions. All right, so let's make this a little bit more complicated. We did 1 dice roll. Let's try 2 dice. What if you're playing Monopoly, right, instead of snakes and ladders? Well, we got outcomes and we got expected relative frequencies. And for 2 dice, those are the expected relative frequencies. Can't roll a 1 when you're rolling 2 dice. Can't roll a 13 when you're rolling 2 dice. There's only one way to roll a 2. You got to roll a 1 on the first. You got to roll a 1 on the second. There's 2 ways to roll a 3. You can roll a 1 and a 2, or you can roll a 2 and a 1. There's 6 ways to roll a 7. That's actually the mode for dice rolls. So you can roll a 1 or 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, or 6 and a 1. 6 different ways to roll that. So we can calculate the probabilities for a 2 dice roll. And once again, we take a look at the possible outcomes divided by the total possible outcomes. So in this case, there are 36 possible outcomes. If you summed up all those frequencies, 36 possible things that can happen when you roll 2 dice. And in terms of the probability of a 1 being rolled, there's no way to roll a 1. 0 divided by 36 gives you that 0% chance. Snake eyes, you only have a 3% chance of rolling snake eyes. So you only got a 3% chance of rolling that 2. There's only one way to do it, and there's 36 possible outcomes. So if you're playing Monopoly and you roll the dice and you land on Park Place, does everybody know what I'm talking about, Monopoly? All right. So if you land on Park Place and you're able to buy Park Place, you only have a 3% chance that on your next roll, you're going to be able to buy Boardwalk, which is 2 spaces down. So the chances of getting Park Place and Boardwalk in consecutive terms is only 3%. So next time that happens, just realize how lucky you are. 3 out of 100. And we can do that for all of the different outcomes. And you can once again see that rolling a 7 has a 17% chance. It's the most common roll. Rolling a 12, again, 3% chance. So double sixes, not going to occur very much. Mathematical probabilities. We are not going to be using these for statistics. What we're going to be using is we're going to be using proportions. What proportions? Proportions of this frequency distribution. So if we plot that frequency distribution, that's what it looks like in a graph, right? That's what it looks like in a histogram. And you can see that, once again, what's the relative frequency? For a 1, there's no way to do it. For a 2, you can do it 1 way. For a 3, you can roll it 2 ways. For a 10, you can roll it 3 ways. So again, the height of the bar indicates the frequency with which these rolls typically occur. So again, what does this buy us? Well, it helps us to answer questions, again, that come up in statistics. So let's say that you were playing a new game designed for mathematicians, and one of the requirements of the game, at one point, you have to roll a prime number. Right? So you're playing the game, and it goes, in order to move on to the next level, you got to roll a prime number. So you're like, all right, well, I got to roll a 2 or a 3. 1 doesn't count. A 2 or a 3, a 5, a 7, or an 11, right? Numbers that can only be divided by themselves in 1. What are my odds of rolling a prime number? And again, you take a look at this and you say to yourself, what do I do? Do I add all these up? Do I multiply them? Do I just take the biggest one and that's my chances of getting at least one of those? What do I do with these numbers? What do I do with these decimal places? That's what we want to avoid. We take a look at it in terms of proportions. And in terms of proportions, once again, this represents everything that can happen. It represents every possibility under the sun. And all we want to do is we want to say to ourselves, which are the ones that I want? Which are the ones where I win? Well, I win on 2, 3, 5, 7, or 11. So then you say, what is that proportion of the whole? And that's your chances of rolling a prime number on your next turn. And we can do this for any amount of dice rolls. So I calculated this out for 5 dice roll outcomes. If anybody plays Yahtzee, this is one of the major games where you use 5 dice. So these are the outcomes. So there is 1 way to roll a 5. You got to roll a 1, a 1, a 1, a 1, and a 1. There is 735 ways to roll a 16. So you could roll a 1, a 1, a 1. No, I'm not going to go through all of them. But anyways, 735 ways to do that. Only 1 way to roll a 30. You got to roll all 6s. And if we put that into a frequency distribution graph, once again, we can see that this represents all of the possibilities. It literally represents everything that can occur. And if we wanted to know what's the probability of rolling 12 or less, if you're going to roll 5 dice and you need to roll 12 or less, what's the probability of that occurring? Well, the probability is that proportion, that blue section of the distribution. And if we wanted to know what's the probability of rolling a 23 or higher, once again, we don't have to do the math. We don't have to figure out all these complex calculations. We just have to figure out what proportion of the curve is that blue area there, which is 23, 24, 25, 26, 27, 28, 29, all the way up to 30. And then lastly, if we wanted to know what's the probability of rolling less than 12 or 23 or greater, that would be the proportion that we're interested in. So that is why we're going to be using proportions rather than probabilities. It just suits statistics much, much better. Now, you're probably looking at me going, well, that's great. This is great. We're going to be using proportions. But this isn't exactly a simple calculation to make, right? This isn't exactly something where we can just kind of look at this and say, oh, of course, 17.5%. You know, that's what that blue area is. So why are we moving to proportions? The reason that we're doing this, and you kind of see it right here, is that in this universe that we live in, and in psychology in particular, there is one frequency distribution that comes up over and 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 over again. And it is the normal distribution. It is also commonly referred to as the bell curve. So this is an example of a bell curve, so-called because it looks like a bell. And this one distribution comes up over and over and over again in statistics and in psychology. So luckily for us, other more well-educated mathematicians have done all the heavy lifting and have figured out everything that we need to know about this distribution, and then have basically calculated out the proportions that we need to have. So in terms of us calculating these things, we're never going to do that. So get into the habit of thinking in terms of proportions. And basically what we're going to learn how to do is we're going to learn where to find these proportions, because the math and all this sort of integral calculus and those nasty functions, that's all been done because this distribution happens over and over and over again, especially in psychology. So get into the habit, this is the last thing I wanted to cover today, get into the habit of thinking proportions of a distribution, because as we're going to see, this one distribution has been figured out because it comes up over and over and over again. All right, so any questions on your intro to probability? All right, so just another reminder, make sure that you stay up to date on your pre-test, your post-test. If you don't get 100% on your pre-test, complete the MyStat Lab study plan. Go to the Quiz Me option, but make sure that you're earning those mastery points. And anything that is from any of the new pre-tests, their due date will be right before exam number 2. And I will be updating your scores for your first pre-test. I'll probably get to them tomorrow, so they haven't been updated yet. So I'm going to update them in Canvas at some point tomorrow. So you'll have those final updated scores. But again, make sure that you're taking advantage of this. It's great to maximize your grades, but it's also great as just practice, just to do those questions a few more times, try it a few more, give it a few more opportunities. All right, other than that, we don't have any, I don't believe we have any homework. Double check the syllabus, but I would have had it up here if we did. But I think that's it for what I wanted to cover today. So let that idea of probability sink in. Think about it in terms of proportions. And when we come back for next class, we'll see how to actually calculate and find these proportions so that we can continue to do stats. Other than that, I think it's an early day, not much to practice. So if everybody wants to call it an early day, feel free. If, on the other hand, some of you want to call me over, maybe talk about your exam or anything like that, we can do that as well. But I am done what I wanted to cover today.